So now we're going to look at modeling with trigonometric functions. So let's start with our first example. The tides of Cape Capeston in New Brunswick change the depth of water in the harbor. On one day in October, the tides have a high point of approximately 10 meters at 2 p.m. and a low point of approximately 1.2 meters at 8:15 p.m. A particular sailboat has a draft of 2 meters. This means it can only move in water that's at least 2 meters deep. The captain of the sailboat plans to exit the harbor at 6 p.m. Can the captain exit the harbor safely? So first of all, we know at 2 p.m. the tides have a high point of approximately 10 meters and a low point at 8:15 p.m. of 1.2 meters. So let's first start plotting those points. So let's assume at 2 p.m. that's going to be time 0. So at time 0, we have a height of 10 meters. Then our low point, which is at 8:15 p.m., that would be a time of 6.25 hours after 2 p.m., and that has a height of 1.2 meters. So at the moment, we have half of our sinusoidal function. So if we were to continue this graph based upon the only 2 points that we have, the next time the tide reaches the high point of 10 meters, so it would be approximately 12.5 hours after 2 p.m. And again, that's based upon the only 2 points that we have. So let's determine an equation for this sinusoidal function. So I'm going to go through the same few steps when determining equations for sinusoidal functions. First of all, I'm going to look for the axis of the curve. To determine the axis of the curve, we're going to take the average of the max y value and the minimum y value. So for this example, this would be 10 plus 1.2 divided by 2, which would give us an axis of the curve at 5.6 meters. So this gives us our Q value of 5.6. Next up, determine the amplitude. The amplitude is the subtraction of the maximum minus the minimum divided by 2. And for this example, we would get 4.4 meters. And the amplitude will give us our A value for our sinusoidal function. And on a graph, here would be our amplitude. Next up, determine the period. And we see one complete cycle takes 12.5 hours based upon the 2 data points that we have. And this helps us determine our K value. Our K value is equal to 2 pi over 12.5. And if we simplify that, that would give us 0.16 pi. That's 2 divided by 12.5. And finally, we need to determine our phase shift. And our phase shift depends on which function we're using, sine or cosine. If we are using cosine, we see our graph already starts at the maximum. So we would have a phase shift of 0. If we plan on using sine, we need to determine the value for our phase shift. So let's say we go back to here. That's 1/4 of the period. So if our period is 12.5, 1/4 of 12.5 is 3.125. So our phase shift, if we start here for sine, that would give us a p-value of 3.125. That's 1/4 of the period. Or if we take half of the period plus 1/4, we can use this value here for our phase shift. We're starting at the axis of the curve and going to a max. And at that point, we would give a phase shift of 9.375. So that would be 6.25, where we started, plus 1/4 of a period, which is 3.125, would give us 9.375. So therefore, a phase shift for sine could be either 3.125 or 9.375 for sine of theta. So now let's determine our equations. So first of all, let's start with our cosine equation. So the height of the water in terms of time would be 4.4 cosine 0.16 pi, that's our k value, times t, plus the axis of the curve, which is 5.6. If we chose sine, we can have it as 4.4 sine 0.16 pi bracket t, and we're doing the minus 3.125, that would be plus 3.125 plus 5.6. Using either formula, we should now be able to answer the question. So let's go back to our question. Can the captain exit the harbor safely at 6 p.m.? 6 p.m. is 4 hours after 2 p.m., so we're going to sub that into our equation and see whether or not the draft of the sailboat, we notice the draft is 2 meters, whether or not that can pass through the harbor. All right, so we sub an HF4 into either the sine equation or the cosine equation, and it shouldn't matter which one you use. And when I tried them both, I ended up with 3.73 meters, which is definitely deeper than the draft of the sailboat, which is 2 meters. So therefore, the sailboat can make it through the harbor safely at 6 p.m. So example 2. The following table shows the average monthly means of the daily temperatures in Hamilton, Ontario. Each month's average temperature is represented by the day in the middle of the month. So using an appropriate sinusoidal model, estimate the average daily temperature on the 200th day of the year. And for this example, I would take the lowest day I see first, and then the highest day I see first, and use them as my reference points to determine the sinusoidal equation. So we see the lowest day is on day 15, and it has an average temperature of negative 4.8 degrees Celsius. So that's going to be my lowest day. The highest day occurs at day 197 and has a temperature of approximately 21.9 degrees Celsius. So this would be half of the period for this function. And again, we could continue this onwards and draw the other half. But let's try to figure out the equation with only the half piece here. So first off, let's get the axis of the curve. And in this example, it's going to be 21.9 plus negative 4.8, all divided by 2, which gives us an axis of the curve of approximately 8.55 degrees Celsius. So this tells us that our Q value is equal to 8.55. Again, that is the line that divides this sinusoidal function into two pieces. So y equals 8.55. Next up is the amplitude. And the amplitude is the subtraction of the max minus the min. And in this case, we'll get 13.35 degrees Celsius. And that gives us our A value for our sinusoidal function. And again, the amplitude would be the point from here to here. Now that we have the amplitude, let's determine the period and our K value. And for this one, I'm going to assume that the period is 365. And of course, that refers to 365 days, the number of days in a year. And if that's the case, our K value then is going to be 2 pi divided by 365. And finally, our phase shift. And I would just take our diagram. If we wanted negative cos, if we wanted to do cos flipped around, we could start there at 15. If we want to do cos when it normally starts at the max, of course, we can start at 197. For this one, it would be a bit trickier if we want to do sine. Sine, of course, would be right here. That would be the midpoint of 197 and 15. And the midpoint of 197 and 15 is 106. All right, so now let's state our equation. So our equation for the temperature. We have the temperature in terms of time t. If we're using cosine, that's 13.35 cosine of 2 pi over 365. And we have a phase shift, so it's t minus 197 plus 8.55. Again, if we want sine, that would be 13.35 sine of 2 pi over 365. And that would be t minus, and in our example we said that was 106 plus 8.55. In either case, if we sub in our value, so this question wanted to know the temperature on day 200. If we sub 200 into either of our equations, we end up with approximately 21.88 degrees Celsius. So now I'm going to show you how to use Desmos to determine the equation of a sinusoidal function from a table of values. So you can either access the Desmos graphing calculator using the web app or download an app to your tablet or phone. On the plus or the add item icon, select a table, and then in the table enter your X and Y data values. Once complete, you're going to click on the magnifying glass with the plus symbol or the zoom fit symbol, and that will show you all your data points. In the next cell, you're going to enter your regression equation. So for your Y values, you're going to use Y1, matching your data set. To complete a regression, you're going to need the tilde symbol instead of the equal sign. Then we enter in our equation. So A, go to our functions, and we can either use the cosine function or the sine function. In this one, I'm going to use the cosine function. Then enter in the rest of your equation. So we're going to need a K, then bracket x1 minus p, because remember our data set, the x values are x1. Then we can close off the brackets and plus q. Finally, we can see all the values for our parameters a, k, p, and q. So we see from Desmos, we have the following equation. The temperature at time t is equal to 13.4631 cosine, because I chose cosine, of 0.017144, that's our k value, t plus 159.798 plus 8.26078. So we can see most of our numbers did match. The a value, the q value, even the k value, if you take 2 pi divided by 365, that's approximately decimal 0.017. And when we sub 200 into this equation, we end up with approximately 21.64 degrees Celsius. Evan is riding his bicycle and gets a small nail in his tire. His bicycle tire has a radius of 35 centimeters. Determine the equation of a sinusoidal function that describes the height of the nail in the tire in terms of the distance the wheel travels. So I would start from where the wheel hits the nail. That would be the lowest point of the tire. So imagine we have a tire. The nail hits the tire here at 0, 0. It's then the nail is going to rise to the top of the tire, come back down towards the bottom. So it's going to make this sinusoidal function. So now what we're doing is we're comparing the height in centimeters versus the distance the nail travels, and that is also in centimeters. Well, the height we easily get from the radius. If half of the circle is 35 centimeters, then the full circle is 70 centimeters. And with that, we already know the halfway point. This would be 35 centimeters, which would be the axis of the curve. We also know the amplitude from this picture. We can see it here. Our amplitude will also be 35. That's the distance from the middle to the top of the tire or to the bottom. The next and the hardest one to figure out is the period. Remember, this is the distance the nail travels. So the nail is going to travel around the tire. And to get the distance it travels, we're talking about circumference. So circumference is equal to 2 pi r. And in our example, that's 2 pi times 35, which tells us that the total distance it'll travel in one full rotation is 70 pi centimeters. So that would be this point right here. And that'll help us determine the period of this function. So let's start with the amplitude. The amplitude in this question, we already know, is 35 centimeters. The axis of the curve is also 35 centimeters. So that tells us that our A value is 35 and our Q value is 35. Next up is the period. So the period we determined to do one full rotation is 70 pi centimeters. That's the circumference of the wheel. And this helps us get our K value. Our K value would be 2 pi over 70 pi. And that is equal to 1 over 35. And finally, our phase shift. So depending on what we choose. If we chose negative cos, we'd have no phase shift. So if we started here, we'd have no phase shift. But let's say we want to include one. So if we do choose cos to start the max would occur halfway between 0 and 70 pi, so that would be 35 pi. And for sine, we want to start at the axis of the curve, so right here. That's the midpoint between 0 to 35 pi, so this should be 17.5 pi. Now that we have all our parameters, we can determine our two trig equations. So the height of the nail relative to the distance traveled could be 35 cosine 1 over 35 d minus 35 pi plus 35. Or if we chose sine, that would be 35 sine 1 over 35 d minus 17.5 pi plus 35. And again, we could have chose negative cos, so let's just do that. If I chose negative cos, that would be negative 35 cos 1 over 35 d. There's no phase shift for negative cos plus 35. So you see there are multiple equations that we can end up with. In any case, if we choose h of 150, so how high is the nail once you travel 150 centimeters, we would end up with approximately 49.5 centimeters. So what does that look like? If we go back to our graph, it's saying that once we reach 150 centimeters in terms of the distance traveled, if we go up to here, we hit a point. If we cross over here, that would tell us we're at 49.5 centimeters high. So again, traveling 150 gives us a height of 49.5 centimeters.